All right. Hello, everyone, and welcome to our June Dunder Main meeting of Chicago Python User Group. Before we get started, I would like to point out our code of conduct. If you need some reading material, you can find it on our website at www.chipy.org/pages/conduct. Basically, we ask that everybody be a decent human being to other participants. Yes. We would like to give a quick thanks to our sponsors who make ChiPy possible. They make it possible for us to present this content every month, both in person and virtually. And we appreciate what they do. So ChiPy is a Python-focused community that started in 2003. We were initially a small group that met in bars. We've grown to over 6,000 members, and we are now nationally one of the largest Python user groups in the country. Part of that is possible due to the work of our board members, of which I am one. So in addition to the Dunder Main meeting, we have a number of other projects that we do every month. We have Project Night and Web Guild. Web Guild maintains our website, also provides a good opportunity for people looking to get involved in an open source project based in Python. We have Project Night, which allows people to work together to solve problems. You can bring your own project, or we provide one for you. We have the Buddy Mentorship Program at chipymentor.org, which allows you to say, I want to learn a skill and be introduced to someone who can teach you that skill, who in exchange would like you to teach them something. So it provides a chance for all of us to learn from each other. We also have the lunch break SIG, the algorithm SIG, and the job board on our website if you're looking for a job. This is last month's virtual events. These have already happened. If you would like to find us online, you can find our Slack at joinchippy/herokuapp.com. You can find us at Twitter at Chicago Python, or of course, chippy.org. With that, I would like to introduce our presenters for this month. Peter Phyall, apologies for misspelling your name, and Nick Petrovits. So with that, I will turn it over to you.
Thanks, Heather. Thanks for having us here.
Thanks for being here.
Go ahead and share my screen here. Get to the right slide. All right. So as Heather mentioned, my name is Peter, and my co-presenter is Nick. We're representing Coyote Logistics. Our topic for today's talk is on design patterns and anti-patterns. Nick, you want to start who we are?
Yeah, so we work for Coyote Logistics. We're a third-party logistics firm. Basically, you can think of us as matchmakers between people who ship stuff on trucks mainly and the trucks themselves, since most trucks in the road out there are owned by small owner-operators. So something I didn't know before I got into the logistics industry was that 90% of the trucking market is companies that have 6 semis or less. So if you're a large global firm and you ship thousands of truckloads of freight a day, it's not practical to connect with all of them. So you wind up working with a logistics broker, and that's what we do. There's a lot of cool problems out there for us to solve, and it's been a lot of fun. I've been in tech for 20 years, always gravitated to the data space. Spent a lot of time though as a full stack developer. Today, I am a VP of Data Strategy and Engineering don't get to code as much, but still love to talk about code. So I love opportunities like this. But hey, I was doing some work in IntelliJ today, looking at some Scala code, which is a rare opportunity that I love. But yeah, mostly engineering leadership now, a lot of focus on data science and predictive analytics. And still, my heart always will love and have a special place for full stack development and software architecture. Peter.
And myself, 7 years in technology and data. In my little bio there, I'm missing a word. It says developer, but currently working as a data engineer. Previously was working as a full stack developer, software engineer, data scientist, data analysts, all across the data and technology industries. And one final plug, Coyote is hiring. Specifically, we're looking for data engineering folks, MLOps folks, data science folks. So please feel free to look at the positions we have open, take a look at our company, and hopefully today, with some of the topics that we'll present, we can interest you in joining the Coyote Pack. Okay. So let's get into the first portion of the presentation. So design patterns. This portion of the presentation will review 3 common design patterns. We'll break that down even further into starting with what a design pattern is, but the 3 that we'll go over are object-oriented programming, sidecar, and adapter. Let's start with some terms, though, before we get into things. So software engineering, what is it, and why are we mentioning it in today's talk about design patterns? So software engineering is the discipline of developing computer software products. You certainly have heard the term before, and you've certainly heard of programming, but there's a distinction between the two. Programming doesn't consider engineering elements or engineering skills applied to software. Software engineering does. Obviously. There is an official Institute of Electrical and Electronics Engineers, and they have a definition of what software engineering is, but it's the systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. In other words, the application of engineering to software. And this is important because depending on your level of expertise with Python, with other development languages, programming languages, I'm speaking from experience that, when we talk in the industry about programming, people that are earlier along in their understanding or familiarity with the industry don't really think past what programming offers, right? And there's a world outside of that uses programming, but also engineering, and that's software engineering. So some important distinctions before we move on. Design patterns. Okay, so this is the purpose of the presentation, right? So design patterns, very simply, are recurring solutions to common software design problems. Design problems, right? Designing a program. What does that mean? It means that you're applying a strategy, and in this case, patterns, to solve some problem, right? That needs to some business logic, some business problem that needs to be solved, right? But the concept of design patterns originated in the it comes from the 1970s architectural industry term, but the actual term itself comes from a book that was published in 1995. And before I get to that, why? Oh, and it looks like there's some editing mishaps in our slide here with these scissors. But why do we think of design patterns? Why do we relate design patterns in architecture in the architectural industry to software design or to the software industry? Both professions utilize creativity within large design spaces. Both professions satisfy customer needs, or must satisfy customer needs. Both professions must satisfy constraints and requirements. both professions see qualities such as elegance and the ability for new functionality. So again, depending on how far along you are in your understanding of Python, whether it's professional or ad hoc or just out of interest, when you are learning design patterns, you can think of this relationship between architecture and software design, and there's some overlap, figurative overlap, right? And some literal overlap. So a book was published in 1995 defining 23 design patterns, becomes a best-selling book, a seminal a publication in for this concept of design patterns, and it's published by the Gang of Four. The book's called Design Patterns. These 23 design patterns fall along 3 categories: creational, structural, and behavioral. You can see some examples: factory method, singleton, adapter, decorator, iterator. But today we'll touch on 3. So we talked about what a design pattern is, how it originates, but why do you need it, right? So it's often, and this goes back to what was said on the previous slide, but common solutions to common problems, right? So it's often easier to rely on typical solutions to problems rather than recreate the wheel. That's not just a software engineering principle or a programming principle. That's a life principle, right? Better to use what's out there than to start from scratch. You can think of design patterns as blueprints that can be customized for a particular design problem. Meaning you're not going to stamp out a textbook version for your purposes. You might, but it's often the case that you will need to customize or borrow elements from a design pattern and apply it to your design problem. And then finally, design patterns applied to most programming languages. We're going to focus, of course, on Python, since this is the Chicago Python users group, but do know that design patterns existed before Python. They will exist after Python, but they can also be applied in other languages. Again, conceptually, maybe not literally or down to a one-to-one element. So let's start with object-oriented programming. I'll just be clear for any technicalities later or issues or criticisms. Object-oriented programming is a programming style. I group it in as the first design pattern in quotes because I see it as the bridge to understanding specifically those 23 design patterns that are called out in that design patterns book that I mentioned earlier, right? It's the structure that helps you understand, especially in Python, but in other languages as well, helps you understand design patterns, right? So I colloquially group it into a design pattern classification, but it itself is not necessarily in a design pattern. It's more the structure to understand design patterns. So object-oriented programming, or OOP, you might have seen it in referenced, or you might see examples. We'll go through some examples today, some actual code, some mocked up code. But it's a method of programming by bundling related methods, properties, and components. So if you think of a Python program, a .py script, as an assembly line, at each step in your program, you, again, using the object-oriented approach, you are taking some raw material and applying it into a system component and that then creates a finished product. The object that results from that stage in the assembly line will contain both data, the raw data that you fed in, and some behavior, right? So in the widget assembly line, we'll have the shiny, flashy portion of the the assembly line, right? Where the widget that we sent in now becomes shiny and flashy. So if you turn that shiny and flashy thing into a behavior, and our raw data, or our raw data is our widget, we're applying that shiny flashy behavior to our widget, right, in our assembly line. And that's kind of a botched example, but that's the idea, right? So we now have this object, right, that has the data and this behavior. But a data can really represent anything, anything with properties and behaviors and functions. A person is an object, of course, right? It has properties. A person has properties like a name, an address, where they live, and has behaviors associated with it, right? A person can walk, a person can talk, a person can breathe, a person can run, etc. You might have heard of procedural programming when either referenced alongside object-oriented programming or in contrast to it. The difference between the two is procedural programming considers a program that's structured like a recipe in a series of steps, right? You have functions or code blocks that flow sequentially to complete your task. The difference with object-oriented programming is, yes, there are functions in OOP and object-oriented programming, but the concept that we are considering here is an object that has, again, both data or properties and behaviors, right? So it's more of an encapsulated unit that contains more elements or more things along with it than just a function or a recipe, right? A lot of this is very figurative language, and we'll get concrete with some examples in a minute, and you'll be able to better understand this. One other thing to note when you're thinking about object-oriented programming, remember the primary definition, or the primary concepts are classes and instances. You'll see some of that in a minute, but classes are user-defined data structures. Classes define functions called methods. Methods identify behaviors and actions that an object can perform with the data, the raw data that it's associated with. An instance is just an object built from a class which contains real data. So I'm going to pause there, and we'll switch here to VS Code, the text editor, and I'll show you some examples to make what I'm talking about here a little more concrete. So give me 1 minute while I exit full screen, and I will share my screen, and you should see VS Code here. Okay, so we're inside VS Code, and let me open up my Python interpreter here.
I don't know if we see VS Code. I'm not seeing that at the moment.
Which screen do you see? Or
I still see your slides.
Ah, okay.
There we go. Now I see your screen.
Okay. Can you see?
We got VS Code. You're good.
Oh,
perfect.
Awesome. Let me blow up the texture a little bit. Maybe not too large. Okay. So I'm going to kind of cherry pick some of these comments here. We'll talk about the structure of, let me go back there. I think I lost my window. We'll talk about the structure of the class that I mentioned earlier, the objects, the instance methods, things like that. The main ingredients in object-oriented programming, right? The main concepts. We'll go through that, but do go through the comments in full on your own, and this code on your own in full. We will provide Heather and ChiPy, ChiPy the code examples so that you can reference these outside of this presentation. To hopefully make the concept easier to digest, I've mocked up a silly example, as you can see on line 1. But this is the structure, right? You define a class, right? The class will later become instantiated, is the term, as an object. But you can think of this class as containing the instructions for what the object will become, right? The behaviors and the instances of that object, right? When applied data to that class, right? So line 1 here is the name of our class. That's just the convention. Line 4, and let me actually skip line 4 and just talk more generally about this class. We're using indentation, standard indentation for spaces or a tab. So everything under our class is grouped here, if you see me highlighting. But let me move down to line 18 here to this init method. I heard Heather mention it at the beginning of this call, but she mentioned the word dunder. And if you don't know what that is, or if you do, you do need to apply that dunder method to a class definition. And in this case, dunder, again, for those that don't know, just is a combination of words double and underscore. And so combining that, you get dunder, right? That's the Python convention. But you need the dunder method in it, right? When defining a class. And that's the initialization method that you can provide your attributes for your future object and for your class, right? And so these attributes you can think of as properties that I was mentioning earlier, right? So for the human example, I was providing properties for a human that would be like a name, an address, an age, right? And so for our dog class, we're using the same concepts, right? So our init method will have 2 attributes defined in lines 19 and 20, name and age. And those attributes, of course, are consistent for any dog that is alive. Well, any dog, rather, not alive or dead. But for any dog, it will have a name and an age. And of course, when that class, that dog class, instantiates into an object, dogs can have various names and ages, right? And we'll see that later on, but just to kind of explain that. So that's lines 18 through 20. We have another concept in here, another method called an instance method. An instance method, you can think of, these are like the behaviors, right? So if we're thinking, again, relating back to our assembly line concept, where I mentioned the widget and the shiny, flashy stage in our assembly line, these 2 instance methods are like those stages in our assembly line, right? So this is where the dog, our dog class, will have a description of it. And in this portion of the assembly line, this is where the dog will learn how to speak, or the instructions for the dog to speak, right? And so that, of course, you can get a little more complicated with this. Let me mention one more thing here and go back to line 4. So line 4, what is line 4? Species Canis familiaris, right? That's Latin for the dog species. So line 4 is an example of a class attribute. So as you'll see in a minute, and as I mentioned previously, dogs can have various attributes of, attribute values of name and age, but they have the same attributes, a name and an age. But in this case, with a class attribute, when we instantiate our dog object, or when we create our dog object, that dog object will will be part of the dog species, right? Or it will have a class attribute that is the same as other dogs. And in this case, all dogs are part of the Canis familiaris species. So that you can think of these as kind of like, I don't want to say global variables because that would be imprecise, but you can kind of think of it in that kind of informal way, right? That all dogs under our dog class belong, that have this same class attribute. Okay, so we went over the structure here, but now we want to actually create some dogs, right? So as I'm sure you guys already know, we have our main method here, and we have our instantiation of the main method down here with some more dunder variables and methods. I take that back, not a dunder method. It's our Python variables. Name, if name equals main, then instantiate the main method. And what's going on in the main method? So in lines 35, 38, I'm creating two dog objects. And as I mentioned before, those dog objects have different attribute values, but they have those attributes, right? And let me just show, because I think I've skipped past this. Going back up to our init dunder method, one thing to note here is when working in the object-oriented construct, you'll see this self keyword before other familiar-looking parameters, right? And the self keyword, or in this case, the self parameter, is just signaling that where it's referenced, in this case, this instance method, this init method, that they all belong to this class called dog. It's just a convention that creates association and signals, again, that one, that you're using an object-oriented approach when, again, for Python in this case, but two, that the methods that you are, the instance methods or any other methods that are associated with this class are associated with this class, right? So why do I mention that? Well, you see that it's skipped, right? In lines 35 and 38. We don't mention that self parameter, that self keyword, when we are instantiating, in this case, the dog from a dog class. That's also just convention. But what are provided as parameters are the name and the age parameters, right? So you can see here in line 35, I'm creating a dog named Brody. And let me mention one other thing. You'll see that Brody here is not capitalized, as is Miles in line 38. But if you scroll back up to line 1, you'll see that dog, the dog class, or the keyword, or the name of the dog, the name of the class named dog, is capitalized, right? And if there was another word, it would be camel case, right? So that's the convention. When you're defining a class, the name of that class is camel cased. But when you're instantiating an object, the object is usually undercase. And additional Python conventions like underscores and that apply, right? So Brody takes on a name, Brody, and an age 1. Miles in line 38 takes on the name Miles and an age 4. The cool thing at this point that I mentioned earlier is now Brody and Miles have both properties or attributes and behaviors, right? And we can access those from that object that we created using dot notation. So now if I want to see Brody's name in line 41, I can call my object Brody and her name attribute, and I can print that out. And I'll run this so we can see this, but just walking through this, this helps. And the same for Miles's age, right? Now, if I want to access that class attribute that we were talking about, the Canis familiaris, right, the dog species, for Brody, I could do the same thing, right? So now I can access, you can see that I can access some of this, some of these behaviors that were previously defined in our class, given some data that we provided earlier, right, in lines 35 and 38. So as you can see, it's a very organized way of approaching some code. It's a dumb example, right? But the point is you're able to access information that is from a format that is structured, right? And similar to procedural programming, where you have a recipe and you follow that recipe from start to finish, right? This kind of takes that a step further, because you have your organization of recipes up above, right, in your class definition. But now you can get very specific about what parts of that recipe you need to access, right, or what information you would need to pull out from that object. And so again, it's organized. It's a readable. It's very reusable, and this code, this structure, this object-oriented structure, can be passed around and shared. And amongst those that understand object-oriented programming, it's a very, again, shareable, reusable way to convey or to approach a business problem or some code or whatever your purpose for writing code is, right? Some other things here. If we want to change information, right? So we have the raw data in this example, lines 35 and 38. We have the raw data that we sent in. But now if we want to change some of that raw data on our object that's been created, we could do that too. So if we want to overwrite Brody's age, which originally was 1, we can and pick another number and have that number be Brody's age. We could do that, right, in lines 49, again using dot notation. If I want to change Miles's species to the cat species, right, Felis sylvestris, I could do that too. So it's a very powerful concept that encapsulates a lot but abstracts at the same time, and creates nice organization, and one that doesn't get caught on itself. It's flexible, right? You can flexible in the sense that we can change some of these values around. And then if we wanted to access some of these behaviors from our object, we can do that too. So if I call the description behavior on my Brody object, if you remember, description would return a string message, a printed message, rather a string that then I print. I could do that. And for Miles in line 61, I can also make Miles speak, right? The speak behavior, and provide in this case, a sound parameter, in which case the sound parameter is a string of woof woof, right? And I can make Miles speak, right, in a figurative way of speaking. So yeah, so this is, I don't want to get too far caught up, but I do want to convey, like, it's a very nice way of conveying information in programming, and I can't emphasize it enough, especially when on the road to design patterns. So enough of that. Let's go back to the slides here. Okay. So adapter design pattern. Number 2, what is it and why are we using it? If you work in industry, if you're newer to industry, you will come across this at some point. It is that common of a design pattern. The reason is you have a lot of many companies / all. I don't exaggerate that, but a lot of companies have legacy code, right? They've been around for a long period of time. Technology has changed throughout decades, within spans of years, and what has withstood the test of time in terms of legacy and legacy code will generate revenue for a company, and they'll still use it, right? And they'll make changes according to logic or things like that. But the paraphrased metaphor or manner of speaking is right. Like, if it's not broken, don't fix it, right? So you have this old code that still needs to be run. Maybe you're just updating the front end, but the back end of your code is still the old code, right? But how do you connect those two? How do you connect new stuff with old stuff? And that's where adapter comes in. And it's not even just new and old, right? You can apply this to apples and oranges, right? It's another way to think about it too. How do you connect two things, adapt two things that don't necessarily on the surface look like they can communicate or talk to each other? Another example of this is when you travel overseas, right? You'll usually have an adapter for an electrical plug, right? Because certain countries use different voltages of electrical plugs, and you need an adapter to plug in your hairdryer from the United States in a Chinese wall socket or something, right? It's just kind of a silly example, but it's the idea of taking one thing and allowing it to work with another thing that on the surface doesn't look like they work together. So adapter design pattern is also referred to as a wrapper, where you're wrapping two objects, or rather you have a wrapper between two objects, where one is catching calls, or where one object is catching calls and then transforming that into a format and interface recognizable by a second, right? It's a translator, or it's, again, an adapter, right? You'll also see adapter pattern with the container convention, right? Containers is in Kubernetes or Docker containers, where you'll have an application container and a sidecar container. We'll talk about sidecar later. That's our third design pattern. So I don't want to get ahead of myself, but again, just think of two things: application, your main application, where core logic lives, and then a sidecar application where some other stuff lives. But you need those two things to work together to communicate, right? And so you apply an adapter design pattern to that. One other take on the definition for adapter design pattern is it's just a capability combination of two independent interfaces, right? Two things that are different coming together to work, right? Again, based on some requirements. So I'm going to switch back to VS Code. We will look at a short example of the adapter design pattern, and then we'll move on to our third design pattern, sidecar. You can see it's a little simpler. We're now applying our object-oriented approach. So it's kind of a nice transition here.
And we still see your slides, Peter.
Forget about that.
Same trick you did last time.
Thank you.
Yep.
Okay. How about now? There we go.
There we go. Yep.
Awesome. Okay. Let me start over. So you can see we have some classes. We have multiple classes, right? We have 1, 2, 3, 3 classes, right? And this is great in the way that we've kind of transitioned from object-oriented to our first true design pattern, because we now get to borrow or utilize or apply the convention of object-oriented approach to a design pattern, right? So you can see the first class I have is a target class. The second is an adaptee class, and the third is an adapter class, right? So you can think of the target class as our domain-specific interface, or you can think of it as the main application, or the main container, right? Or target application, or application container. And then you can think of the adaptee as what needs to be converted before it can be applied to our main application or our main target. And then we have our third class here, adapter, and that's what's going to create that bridge between target and adaptee, or main application and sidecar application, or hair dryer plug to Chinese wall socket, or, again, just throwing all the metaphors, right? So let's talk about what each of the classes are doing. The first class, the target class, has in it an instance method request. And it simply just returns a string that says target, the default target's behavior. Under adaptee, the instance method associated with adaptee class is specific request. And you can see that using the latest Python convention, right, syntax, all these are returning strings, which you can see in the return lines here. One other thing to note, going back to object-oriented, you see we have these self parameters, right? These self keywords that clarify or declare the association of the particular method with our class, right? And then finally, we have our adapter class. And so this, you can see the adapter class now has some parameters in the definition, right? And that looks strange, but have no fear. It's pretty explainable. Adapter is taking, the adapter class is applying an object-oriented programming convention or concept called inheritance, and inheriting all of the properties, all of the behaviors, all of the attributes of our two previous classes, right? Adaptee and target. And that's pretty cool because you can borrow from an existing class that you've defined and then kind of create another class that uses that and builds on it, right? And so here, to fit with our understanding of what adapter is doing, adapter is taking both the classes that we've previously defined, target and adaptee, and all the attributes and behaviors of each of those, and applying it under a new class called adapter. And this will be what will translate the adaptee into our target. And you'll see this as an example here. We have a method, kind of moving outside of that. We have a method away from our three classes. We have a method called client code. And we're going to instantiate it down here in our if name equals main. But let's kind of move along to instantiating our target and adaptee objects, right? Lines 41, 45, we're creating our target and adaptee methods that have those instance methods associated with them, right? These return strings that we're seeing. And we then in line 53, we're instantiating our adapter, which again is using inheritance to inherit the attributes, properties, and all that from our two target and adaptee classes. And if I now want to apply to that client code method the adapter object that I've created. Well, and let me run this so we can kind of see this working. It's kind of hard to just explain it, but once the client code accepts our adapter object, you can see that because we've included inheritance, or we're inheriting in our adapter object the target class. The target class has that method request, right? And again, we are able to borrow or take or use that class target instance method and the adaptee specific request method and access them once we, on our instantiated object, access them from our adapter object, which we're feeding into this method client code. And so now in line 36, when we instantiate this method client code, we can access the target request, which then will result in that print statement, which then will call our adapter object. And let me run this. So this is this makes a little more sense because I think I'm losing you guys. But let me run this really quick and show you. So let me go to the line numbers and we can kind of trace through this. So you can see here, we first print client. The adaptee class has a weird interface. See, I don't. I can work just fine with the target objects. Target, the default target's behavior. Client, the adaptee class has a weird interface. See, I don't understand it. Adaptee, this is what it looks like. It's backwards. And then client, I can work with it via the adapter, in which the adapter now translates this string, which was backwards. And now, we can apply that to our main application, right? So the idea is, again, simply we have our target, we have an adaptee. The adaptee has legacy or some sidecar functionality that needs to work in conjunction with our main application. And we can accomplish that using the adapter design pattern. This is a nice example of that. So let me go back to the remaining sidecar pattern here. I'm going to click on this. There we go. There was a lag. So the sidecar design pattern. So kind of moving on from the previous mentions of sidecar that I've already made, let's talk about it now. So you can think of, let me start with the basic term in the visualization. So you guys are all familiar with motorcycles, right? And if you know motorcycles well, you know that there are sidecars that are attached to motorcycles. And if you're not as familiar with motorcycles, you can think of like a motorcycle from World War II, right? That classic piece that was riding along a motorcycle that was maybe holding a general or something, right? But the idea is it's something that is running alongside something else, right? It's a supportive process. It's a separate process that has its own capabilities that can exist, right? And help and provide some functionality. So you can use Sidecar to add capabilities to an application without additional configuration. What does that mean? That's helpful. In the microservice context, you can have functionalities like monitoring, logging, configuration, networking services, functionality that you wouldn't want to create multiple times for multiple applications, right? So you can kind of, in an imprecise way, you can kind of double dip, or you can create efficiency by having these services, these sidecar services, run alongside your main applications and provide the same functionality for those applications, right? So the reasons you'd want to do this, I touched on this slightly, but you don't want redundancy, you don't want complexity, you don't want to jeopardize your main application and create interdependence. You want to create an efficient, functional microservice, right? In this case. So use the sidecar pattern, right? Kind of separate out functionality that is used by all of your applications and have that run as a sidecar or as multiple sidecars. You can also think of it as a way to abstract infrastructure functionality to different layers, right? This is good because this reduces code duplication and creates a loose coupling between services and a main application, which again, to lessen the interdependence and that liability on failure, right? One thing you don't want to do is jeopardize your main application by weighing it down with redundant functionality. I mentioned this earlier, but we can talk about it now. You'll often see sidecar design pattern implemented now, currently, as a container using Docker or Kubernetes. And this is essentially what it looks like, right? We have our main application or our main container that runs our application with the core functionality on the left. And we have our sidecar application that does one or multiple things, configuration, logging, monitoring, etc. And between those two, they share file system, potentially disk, network. And so you have a loose coupling, but at the same time, independence, right? I think that's going to round out this portion of the talk. One other thing, if you reference these slides later, we have some additional resources here on some books on design patterns, the original design patterns book from 1995 and some other ones as well. So yeah, thanks for listening, and pass it on over to Nick.
Cool. Thanks, Peter. So I don't know if you can see my screen here or not. I'm seeing Peter's screen still at the moment. Cool. There we go. All right. So Peter talked a lot about design patterns. I am going to talk about some anti-patterns here. And that was the other half of our talk. So one of the first ones we see here is try, except, pass being misused. So people swallowing exceptions within their exception handlers. Seen it in a lot of code over the years in many different languages, not only Python. But I want to start by briefly sharing the Zen of Python. I'm not going to read through the Zen of Python to you. Hopefully everyone's seen it. If not, a little URL here to go check it out later. Again, it's also going to be in our slides, which we'll share out. But in particular, I want to highlight that errors should never pass silently unless explicitly silenced. And in the face of ambiguity, refuse the temptation to guess. So refuse the temptation to guess, will my application continue successfully or not if I were to silence these errors? So we need to be careful about how we handle that. And, exceptions can be dangerous, right? Some practical anti-patterns to watch out for are we don't want to set ourselves up for failure later. And I'm going to go through a couple examples here. They'll be from some harvested production code of ours that's been slightly harvested and brought into a format applicable for tonight's settings. But, sometimes if we swallow an exception, we might wind up with a variable that's set to none. And when we try to use that, we'll get some issues. Oftentimes, I've seen code log something about an exception, but just letting it continue to cruise through anyways, which will potentially cause some unexpected behavior that we'll have to debug in production one day when we're least expecting it. I'm not going to maybe read through all of them here, but one of the more interesting things is catching base exceptions instead of a particular type of exception that we want to handle. Will cause us to sometimes think we're gracefully handling an appropriate exception that we got or we're expecting, but rather handle all types of exceptions. The other bit that I think is oftentimes missing from code too is handling specific types of exceptions early, like right at startup. So for instance, if we need a configuration file that will be read later when a method's called, it can be valuable to catch that right at startup and make sure, in our main init methods, and init methods that we are validating that everything that we need is there. Are the things we need accessible there? If we're using a database that has stored procedures, well, stored procedures in themselves are included here because I believe they've been in an anti-pattern for the last 10 years or so, maybe longer. But do you have access to them? Do you have access to the tables? Do you have access to the file shares you need, etc.? And are the secrets needed for that all accessible? We can actually catch that and throw exceptions as our container startup if we're deploying in Python to Kubernetes or within other Docker style containers. And we can just crash the program right at that point, right? Odds are those probably aren't going to come back, whatever the system is that's managing that. If it was maybe a build system, we want to have an automated failure of that build and a rollback. We can do something like that and do some more graceful failures if we actually just hard fail the application early. So exception danger here. Those more skilled at Python will probably be looking through this code, and I'll give you a minute to look through it. And there's several glaring problems with this code. You may or may not think the model name Truck Norris model is problematic, but can't tell you what the Truck Norris model does, or I'll have to send Chuck Norris after you. But yeah, there's some bigger problems in here. In particular, one of them is what's going to happen if this exception handler just fails through and we wind up here catching a generic exception and just letting some stuff be set to none. And let's say later we call the predict method on the CLF variable. And what might happen is we'll get an error here, and it's just going to say none.predict. Whoops, none type object has no attribute predict. Right, so everything in Python is a class, and including none is actually a class. And the none class doesn't have our predict method that we had put up on it. So, well, that's interesting. I mean, it looked nice. We had a nice try. We had a nice accept method. And we even had a more generic one if it wasn't an IO error. And in our IO error, we try to load the model again. But interestingly enough, this can also fail. A whole bunch of other things about, or comments on doing things that may fail in the accept handler, but we purposely left some bad code in here. So here's a more correct example of this, right? If we fell into here and nothing happens, we can just raise a custom exception and said at the end of all of our code, it's still not set up right. Well, shoot, let's say this is our main method. The whole Python application is just going to crash at this point in time. And this will get written hopefully out to standard out in the end, at least, or somewhere else that's useful. And we'll know that we weren't able to load any model data and that the program shouldn't even try to continue. So that can be incredibly helpful if we were spinning up a new container in a Kubernetes deployment, see that the containers failed to initialize properly, and they would automatically roll back, and we wouldn't migrate over to the new containers with our latest build, and our application would stay up. If we didn't do that, it might fully deploy nice and happily, and some users start to hit it and get some traffic. And as we're testing it, we realize, shoot, there's some sort of configuration problem that's not letting this continue. So that can lead to some danger. While on that topic, that brings us right into the early programming lifecycle. One of the things we can do there is, like I said, right as the program starts, try to load that configuration and then check all our dependent services here and fail for any abnormalities that might be out there. Once that happens, we enter our main block of our program lifetime, let's call it, and we might be sitting behind an Nginx server or something and processing some data whenever we're called, let's say. So I guess that's really that incoming data here is going to start our method. If we find any data validation problems or anything with that data, again, we can report abnormalities back to the user. Otherwise, if everything works successfully, we can come back with results. So at this level here, we're maybe failing that single request response cycle, or otherwise letting it go through successfully. The risk of letting it come through this way is without having a separate return and response back is, we might get some unexpected results or partial results. And the user might not know that, that save method you think you called swallowed the error, that the save failed to commit to the database, and it looks like it saved, and we returned success. We saved your data, but in reality, we did nothing, and your deposit of $1 to your bank account didn't happen. So that can be exceedingly frustrating. More towards a positive pattern, though, is we really like when people make things discoverable and make services easy to monitor. Like what could be great is if at the same time, some of these checks that we're doing for abnormalities here, what if we wanted to be able to pull those up at any point in time? We could do that maybe by something like a status endpoint. And that will allow services to self-serve information about them and about their health. We can also post these to things like Datadog and whatnot. Prometheus can be a great solution here. I'm jumping out of order through my slide. But what if we could provide things about like which version of the Git commit it was? If it's an ML model, how old is that ML model? Does it have connectivity to its database or a file system or any other external dependencies? When's the last time it's received data? We can report all sorts of information. And it can just be something as simple as like adding /status to the end of one of our endpoints or our web services, and give it maybe just a nice JSON response with that same minimal relevant age, so let the thing know, hey, I'm healthy. So an example of something super simple is, what if the app just went through and decided, yep, I'm healthy, let me tell you that. And it maybe internally did all those checks. And maybe this is if a non-authenticated user took a peek at it, what they'd see. And, maybe someone more authorized within the environment would be able to come in here and see that, oh, here's a lot more detail about it. So I'm logged in, I'm an administrator on the site, and I can get all this additional information. Or maybe if you just don't care, you can get this as well. So in this particular case, we could see that we have live data as of this time. The service is healthy. We have 2 different versions of the model here that were trained on different dates. And even, maybe here's our commit hash. This is really from a fake version. We wouldn't have a model A and B, but still, I don't know, decided to hash out some of the details in here just because they're not relevant to the discussion. But, these could be Git commit hashes, Git repo directories, all sorts of different things like that. So we'd be able to figure out, like, how old was our infrastructure as code this is written on? What's the source repo this came out of, and what version of our build system did it run on? So we could check our services and make sure, like, are these what I expect them to be? Hey, I thought we turned the next version of the build on the config management system, but we're still facing, it doesn't seem like we're getting the new behavior out of the platform. Oh, well, weird. That doesn't match the source, the hash of our source code I expected it to. All right, well, clearly that tells me something's wrong, or I need to look into it, or, these predictions seem weird. Oh, wow, that model's trained 11 days old compared to the other one. Okay, something's broken there. Why is this not retraining? And why are we not getting the latest trained version of the model? So putting a little self-service information can be a super handy little pattern that can help us survive when we've gone through some of the other anti-patterns. Another anti-pattern that we often come across is code that's not dry. So what does it mean to be dry? It means don't repeat yourself. Pretty simple. So in some code written, like definitely the code I wrote when I was more junior, I'd probably try to have a lot of methods that look the same, or maybe copied and pasted code from one application into another application so it could be reused. Things like that. We really don't want to do that. There's a whole bunch of reasons behind that. For one, if we repeat ourselves, every time we have to update that logic, we don't have to update it just in one place, but we have to update it everywhere we copied and pasted it. So maybe it's in 3 different services, all need to be able to, let's just say something simple, like make that status endpoint. If I had that produced in like a library or something else, I could reuse that. Or if it was deployed as a sidecar, for instance, I'd get that functionality again and again without re-implementing it across all of my programs. Or if different classes within my code have similar functionality, I shouldn't have to repeat that. So it just becomes a maintenance nightmare, and inevitably we miss updating it in one location or another, and our implementations wind up varying, and we get code drift. I think I already went through those points. But on the flip side of that too, remember not to optimize too early. There is such thing as premature optimization. You aren't going to need it is a common acronym. So if you're doing something for the second time, it might not be ready to fully optimize, but for sure, if you find yourself doing it on the third time and it's going to be a pattern that you repeat again and again, be sure to optimize it. So maybe not everything needs to be packaged as an API or a Python package, and we can wait on that until we prove that we're going to need it again. And I guess I blew through my slides really quickly here, but a quick thank you. And I guess now is a good time to see if we have any questions.
Well, thank you both for the presentation. I was not aware of the history of design patterns in relation to architecture as well as software engineering. I had a quick question. I find it interesting that you mentioned object-oriented programming as an example of a design pattern, because it's more or less structural, creational, and behavioral.
Yeah, that's a fair point, and that's kind of the nebulousness of how you classify it. Again, it's technically not a design pattern. It borrows from a lot of design patterns, but I primarily see it as the bridge to help one understand design patterns. In the case of Python, because there are a lot of design patterns that are implemented using object-oriented approaches. But yeah, it is an interesting, I hadn't thought of it the way that you mentioned it, right? Kind of like borrowing in the three classifications according to the Gang of Four. It does kind of borrow from each of those three groups, and it's a good point.
You have the object, which would be structure. You have the init method, which would be creational, and then you have behavioral, which in Python is just your methods, or in other languages you have getters and setters. And
yeah, that's right. And in the object-oriented, your instance methods. But yeah.
So I know a common problem that I run into, probably other people as well. The problem of separating a monolith into microservices.
Yeah.
You mentioned the adapter and sidecar patterns. Are there any other design patterns that you find are immediately relevant to solving that kind of problem?
I'll grab that really quick, Peter, and if you want to elaborate too. Yeah, I love to use a strangler pattern in that as well. Why is that useful? To contain a lot of functionality and prevent it from leaking out. So if we can make our new microservices and put the proper contracts we want in there, and then prevent other services from calling that monolith and hide that, I guess it's more of a facade pattern really at that point, potentially too. But if that new microservice can actually strangle and contain around its data and all the business logic or business workflows, ideally, that it's going to serve, it can be a really useful construct to hide some of the ugliness that's in that older legacy code and make something that's easier to maintain. I think about a very, very complicated service I worked on some years back in the financial industry. And there was this bit of code that made future predictions on the stock market. It was incredibly ugly. It wasn't super fast. We called it a lot, but we could distribute that across a lot of machines, hide it behind a facade, basically, and bring those workflows into a more modern UI and strangle all that functionality behind the service and make it pleasurable to interact with. But the risk of breaking that code was so high, no one really wanted to change it. It's the type of industry where if you make a change in that code base and it's wrong and you deploy it to prod, well, you just cause a resume generating event and you'll be walked out of the office in minutes. So so the risk to changing that was really high. So, it was a great pattern to mitigate some risk. Peter, I don't know if there's anything you want to
No, yeah, Strangler is what came to mind. Yeah, I agree with that.
Nice. So I've got to ask, Nick, you mentioned as an anti-pattern, premature optimization and catching base exception. Do you have any examples of either of them biting you?
Do I have examples of them biting me? I'm sure I do. In that particular code base, we had a problem, I believe, where the model was not getting instantiated. And in that case, we were just catching exception data that we didn't really use, and we printed an error, I think, to the logs ultimately and let the program continue. So it's like this thing's starting up and it looks like it's running, and it's like, well, that's silly, right? Because we could have avoided that. Other cases where that's happened to me, there's one a really long time ago that there was this error that like never happened, and I can't even remember exactly what the scenario was, but just randomly we get these failures, and it wound up being because the code base had its own custom exception type defined, and this wasn't in Python at the time. It was in a different language, but they had only changed the capitalization of the exception method.
Ooh.
So I had been working on this code, or the exception class. So I'd been working on this code base for, I don't know, probably 6 months. I was a consultant, and I didn't even realize that they had a custom exception class. Like they had used a lowercase e in exception instead of uppercase e. And I wrote my exception handlers as I always did. I think I had a script, so I would just type a shortcut and it would automatically fill in what I needed. And in production, there were these weird things happening that I could never reproduce. And it wound up being that I was handling all the exceptions, or the wrong type of exceptions, or missing something. It wound up being really weird. I mean, there's so many mistakes that were made in that code base between like hiding functionality, the abstractness of like slightly capitalizing, slightly changing the name, but making the name look like something else. It just made it really hard to figure out. I think it probably took me at least 3 or 4 days, probably the better part of a week, to figure out like what was actually going on. It was just one of the biggest time sucks I think I've ever been pulled into debugging an application. So there was a lot of lessons I learned about clean code from that one, and handling the right type of exception. I'm sure there's been others, but that's probably the most painful one I remember. That's top of mind.
Fair enough. So it looks like we've got a question going back to the question about monoliths and microservices. For the try exception and the end the program on failure, do you think adding a retry object on the resource, since due to the progression from monolith to microservice, sometimes the external resources are not available or overloaded?
Yeah, that's absolutely great. Especially when we deploy in the cloud, right? The cloud is very ephemeral, and things may or may not be there at any point in time. It's not like our on-prem data centers where we optimize everything for exactly how our workflows would be, and things never moved around between resources, at least before VMware and stuff. Interestingly enough, like I like to rip on Microsoft a lot, but they have a really good patterns and practices document out there. If you were to Google like Azure transient fault handling, I think has one of the best put together pieces of documentation I've found to address retries, and even some best practices around like do a real fast retry right away, then fall back to like 5 or 10 seconds, then fall back to 30 seconds, and then take a minute off, and if it still can't connect, then fail fatally. They have a whole bunch of practices of different classes of like transient faults and transient failures, and how long to wait for them. So yeah, definitely infrastructure failures happen. I think a lot about queuing systems and, things that use a message queue of some sort. And that can go really wrong and really ugly if there's a really short transient fault and you suddenly clear all your messages out into the dead letter queue or whatever it may be. And now you got to think, shit, how do I go back and get that all programmed into rerun? It can be really difficult. So definitely like, oh no, 3 failed in a row. All right, maybe I should stop and there's a different error here and have some code to check and make sure my environment's okay. All right, it's not. Let me make sure it comes back up before I continue processing and just dump everything to the dead letter queue or whatnot, and have to make some poor developer, usually myself or someone else on my team, go back and reprocess all that data, or just tell the customers or whatnot, business users, sorry, we lost it.
So, all right. Our next question, do you feel that there are certain design patterns that don't work well with Python versus other languages? Or do you find them to be fairly language unspecific?
I would answer that in 2 ways. One, first, generally conceptually or concepts is the main point of the design pattern. Speaking from experience, before I joined Coyote, I learned the adapter or the wrapper design pattern, applied it using procedural programming in a very naive, unsophisticated way. But the concept was still there. We were applying to interface with machine learning code, prediction code. We had a wrapper that interfaced with that machine learning code, and created that translation to allow for that machine learning prediction to function. So I would say if necessarily you're running into a language block or a language specificity block, I think the concept can still be carried out. Now, specifically, when I think about kind of unnecessary design patterns in Python or design patterns that don't translate nicely to Python or conceptually to Python, I would think of the singleton pattern. And I think of in Python, you have the module concept. And when you load a module in Python, that's essentially a singleton pattern. So you don't necessarily need to create one using Python for that instance. For that example, you have a module, a Python concept or an object that kind of does something, to me, very similarly to a singleton design pattern. But yeah, that's what comes off top of mind, those 2 points.
Yeah, it was the singleton was what came off top of mind for me too. It was interesting when I first started using Python, I'd use singletons a lot. And I think I started writing when I was like, someone saw it and like, what the heck are you doing? That was the feedback they gave me, like, it's already built in. I was like, oh, all right, cool. Read the manual. I didn't put this one in the slide deck, but not reading the manual can also in some ways be an anti-pattern.
Yeah.
I think a lot of times we just quickly search the internet and, by default, something like Stack Overflow or something else will pop up. They'll have an answer to our question and we might quickly jump to whatever that answer is there. And the answer might be good, and it was good for the question that was asked, but are we really asking the same question with the same assumptions? Like if it were my question and I asked it and I got that answer, maybe I would have said, but what about in this location? And they would have worked with me through Stack Overflow to refine it. So we do need to be careful that we don't just necessarily take the first or the common answers we see out there, and we do go back and read the manuals. And, sometimes there is something that can be found that's quite interesting there. And I think the modern pressures of work and delivery, and there's always way too much work on our plates. We've asked to be full stack instead of just specialized in one particular area, has really put a lot more pressure on us to try to just get things done really quickly. But I think if there's a framework or something we're using really frequently, there's still a lot of value in getting deep in-depth knowledge of it. For instance, if a lot of us in the Python world find ourselves using pandas quite frequently, there's a lot to pandas. I don't think, and it takes years of using pandas to truly become an expert at it. And even then, a lot of people who've been using pandas for a long 5+ years, let's say, might not feel that they're fully an expert at it. And just because you just start to at that point realize how much you don't know about it. So I think it's still okay to go back and read the manuals. They've unfortunately gotten worse over the years because less of us read them. But still, sometimes, there's can be some good stuff in there.
I would just jump on that and add to it by saying, not a caution, but just pointing out what we know as Python developers in this community, right? Which is Python is an abstracted language, and kind of wrapped up in our talk here is that point, or underlying our talk is that point, right? Which is whether it's Stack Overflow versus the manuals, or it's the various design patterns that we discussed, there is a level of abstraction rather that Python already applies for convenience, but also potentially for detriment, right? And so that's why it's important to read the manuals. That's why it's important to understand the concepts of the design patterns so you can apply, right, or the language of design patterns, right, of the structure, like an object-oriented approach, so that you can apply accordingly and troubleshoot accordingly and know exactly what value you are getting from the tool or the tools that you are applying to solve the problem.
Sounds good. I guess one last question. Do you have any calls to action for our community?
Trying to think. Yeah, probably just keep hanging in there, keep being a community. I think one thing I love about Python a lot is just it's much more community oriented, I think, than any of the other programming languages I've ever used. Some of them can be a bit cliquey. I feel like in the Java world, it's very split up and very segregated by, what, am I a Spring Boot type person, or do I use some other framework? The .NET community's gotten better over the years. The C and whatnot communities are all pretty closed off and a lot more older school. But I think I find the Python groups to be the most energetic, most engaging, and just let's keep doing that. Like I personally fell out of touch a bit with the Python community over the last 2 years in the pandemic, trying to jump back in and be more involved again. And I think the impetus of it for me was seeing that ChiPy was back to in-person events, and I know we wound up remote today, and that's fine. It's the new world we live in, that sometimes we're going to be remote, sometimes we're going to be in person, but just don't let our time away from each other physically prevent us from continuing to be a community. And that's one of the bits about Python that I love. So yeah, I encourage more people to come out here, talk, be a part of the community. Anyone can do it. And Python is just an awesome language with a bunch of awesome people using it. And I always really enjoy talking about Python over some beers at the bar, and we'll miss that part of it today, which is fine. But looking forward to it in the future.
Fantastic.
I think I like that. That's a very hopeful message, and I don't mean that in a disparaging way. I think that's right. That's kind of been my experience as well. I think the community's engaging, and I would just echo that. Right, just stay engaged and continue sharing and continue applying your understanding. And kind of further refine that. And you're already in a supportive, community that is very democratic in many ways. Similar to what Nick was saying earlier about siloed communities or kind of closed off communities that are cliquey or very us versus them kind of approaches. So yeah, I like that. I want to echo that or foot stomp that yeah, keep up the engagement. I think it's been really, this is my first ChiPy event, but I think this is very neat to see the extent of the questions that we're seeing in the comment section here, the reach and the influence of the group, right? That you were mentioning earlier, Heather, about how it's become, ChiPy has become one of the largest Python user groups in the country, and it's just so it's optimistic and inspiring. So yeah, thank you. I'm feeling very inspired in the current moment, just kind of thinking about this experience. So yeah, keep up the engagement.
There was just a comment in the comments. I don't know if everyone who's watching the event live or not can see the comments, but it said statement, don't be afraid. Oh, there you go. Cool. Yeah, statement, don't be afraid of failure. You learn far more from failure than success. This is something I tell my team all the time, is like, go out there, try things. We got to screw up from time to time. If we never fail, it means we're not trying, we're not learning. Excuse me. When we're at the most basic level of human ability, right? When we, I don't know, not the most basic, but, let's say we learn to crawl or walk, right? If you had the joy of watching a baby do that, what do? They fall flat on their face for quite some time before they learn to crawl around, right? Like, we learn by failing. That's the best way to learn. Like, sure, you can learn a little bit from listening to people talk, but hopefully it's more of an inspiration to get you to go out there, try it yourself, get stuck, ping this ChiPy Slack group, and someone someone I know will be there to answer your question. I know I personally have asked some tough pandas questions, where I had some performance issues I couldn't figure out, and I found a ton of help from the ChiPy group. And these were like crazy, stupid questions. I was like, no one's going to know how to do this, right? And of course, someone somehow did, and helped me get to the bottom of what I was doing wrong ultimately, and walked me through, some of my failure, and helped me ask the right questions to eventually read the docs, stumble on the right solutions. So yeah, don't be afraid to fail. Don't be afraid to ask for help too when you've banged your head against the wall long enough and you're like, man, I just can't figure this out, right? It's okay to raise your hand and say, hey, I've been stuck here, can't figure this out, tried a whole bunch. These are the things I tried. What am I potentially missing? Or how am I looking at how could I look at this problem differently? And get some help from the group. The ChiPy group is awesome, and it's a great community to be a part of.
I would add one more call to action. I was thinking about this as Nick's comment here just inspired me, this thought. But I would also say simplicity, right? Simplicity is not an enemy of yours. I think simplicity often is grouped or synonymous with lack of sophistication or naivety or inexperience. But while you are failing, make sure you can fail at small, simple, benign things. That's thing one, and that might sound obvious, but more on simplicity is when you apply a simple example, and Python makes this really easy, right? You can just think about the problem in very basic Python objects or structures, right? Or the core concept of an idea. When you break something down into its component parts or into a simpler base parts, you understand the concept easier. I think that's a universal trait for learning, right? Is you have to start off learning about something in a very naive, simple way, and then you add layers of sophistication. Certainly there's some motivation when you kind of dump yourself into the deep end. That can be motivating to some or to all. But again, yeah, I would focus on there's the acronym, right, of keep it simple, stupid. And I don't think that's a bad thing. And I think that we should all do more to lean more into simplicity, not to be confused with, again, lack of complexity or I'm failing to think of the word that I just mentioned, naivety, right, or inexperience, but see that as a good thing, that if you can explain something and its component parts, or using simple materials or simple examples to better explain something, that's a good start.
Peter, you reminded me of one of my both biggest failures that happened too late, but in retrospect, at this juncture, happened very early. It was also one of the best mentoring and toughest feedback moments I've ever had in my career. I had just graduated college, had been an intern for 2 years, and had a mentor at my new job. And I probably spent the better part of 2 or 3 months building this application in C++. And it used like net named pipes to communicate across different processes to parallelize work, and it was on different machines. And like I was so proud of this architecture and everything I'd built. Wrote a ton of code. And back then, we didn't have all the cool Git tools we have today. And I think I had to print it out 2 pages per sheet, box, double spaced, double sided, and give it for code review. And I remember staying late at work the last day after I finished testing it, printing it out, leaving it on this mentor of mine's desk for code review. And he's like, "Hey, did you read it yet?" Because I need, the next morning I asked right away, "Did you review my code yet?" He looked at me like I was crazy. Of course not. I just got in. Chill out. I'll get back to you in a day or two. So he eventually gets back to me like super fast. I think the next morning I came in and it was sitting back on my desk. And he says, he just left a Post-it note on it and it said, "We need to talk. You need to rewrite." Or I think it said, "We need to talk." And his response to me was, "We need to rewrite it." Like, throw it all out, right? So at the time, like, fail fast. What I should have done was make a design, gotten a design review from the person who would later code review it. The reason why I say it was still failing fast was because this happened to me very early in my career. And, he gave me some really candid feedback. So I know the book Radical Candor has been popular the last 5 or 6 years, probably, right? We just actually went through a thing where a lot of the leaders at our company who hadn't read it yet, we asked them all to read it and talk about it and whatnot, and had the company come and talk to us too. But like, looking back at it now, he gave me this really radically candid feedback of, there's nothing wrong with your code, but you need to rewrite the entire application. And the reason why is like, did I really need to do all this process creation and inter-process communication and make the application so complicated? Like, he had me re-whiteboard, well, what does this thing really do? And break it down into, Peter, your point, really simple chunks. So I explained it to him really quick. He goes, "All right, well, there's your design. Rewrite your application, please." Interestingly enough, that original application took me months to write. Took me, a quarter of the time to rewrite. I think I rewrote it in a week or two. And it was way more maintainable. Like, there was a tenth the code that I probably wrote the first time, right? And, what I've learned at this juncture is we all have an error rate that every so many lines of code, we write a bug in general, right? And depending on our experience level, we can get away with potentially, and our attention and other stresses in our life at the day, we can get away with more lines of code before we write a bug. But, one of the best ways to reduce bugs in code is just simply write less code. There were probably a whole assortment of bugs that I just didn't run into in testing that super complicated version that just never existed in the new one because complexity was lower, the code count was lower. So there's a whole bunch of lessons like that stayed with me, fortunately, my whole career about keeping it simple. And I was fortunate that, like, right at the start of my, full-time professional career, I got some of the harshest feedback I could get and just failed really hard. But I actually kind of recovered pretty fast too. When you look at, 20 years later, like, that memory has been there. It's helped me give feedback to other people, help me realize, oh wait, like, you're junior, you probably don't know how to design something or build something like this. Let me ask you, did you design this right before you get started, right? And it's helped me so much in my career. And I was so fortunate to have someone who was that willing to give me that candid feedback. And yeah, I mean, I'll tell you immediately, I was probably incredibly upset and frustrated, and like my emotions were probably through the roof of unhappiness. Probably hated the guy who gave me the feedback too. But at this point in time, he's, you know, one of the best mentors I've ever had. And that was one of the best lessons I've ever had in my career, even though it was just, you know, threw me right on the floor. And like my pride, you just basically dumped it in the garbage can. You know, person who shall not be named. But yeah, it was some of the best career advice I ever got. So fail fast, but also just don't be afraid to fail. Like that helped me for everything I did later. And I only would have learned that lesson had I failed in such a big way.
Yeah, and keep going from the failure, right? I think there's often time, you know, there's a grieving, you know, period, and as you become more experienced, you shorten that grieving period maybe to mere seconds or minutes. But certainly allow yourself to grieve, right? Be pissed, you know, say a couple swear words, give yourself a half a day, whatever, you know, but you'll find that the more that you fail, the less time you're going to need to grieve or to kind of vent or to kind of get those emotions out and then refocus yourself. And at that point, when you start recognizing those cycles are shorter and shorter, you'll know, right? You'll have that confidence that like, yeah, I'm moving in that right direction. I know, because you are failing fast at that point.
Yeah. 20 years in, it's a quick middle finger at the computer.
Yeah.
It's my fault. Right. Whatever. Let's move on and fix this.
Yeah. Everyone has different ways of expressing, but no, it's a healthy, right? Obviously, I'm not condoning violence, but no one is. But certainly don't hold on to it. Convert that into shorter cycles to do better, right?
No, we're all facing it. We all make mistakes.
I still yell at the computer all the time, like, you know, but it's more so you internalize the mistake. And I don't mean that in a negative way, because when you internalize something, that's the opposite of what I'm saying. But you recognize that user error takes up more of that than you know, the thing that you're yelling about or the person that you don't like. But converting that, and the more that you fail fast, the more that you'll realize like, oh, it's something I did wrong, or that if there is a legitimate problem with something or someone that is not you or your work, that you'll work constructively to help either solve the problem or that to be part of the solution. And I think that's another, just opening up so many cans of wisdom. We're kind of inspiring each other here, but that's another thing is, as you're failing fast and you're shortening those cycles and you're you know, grieving in shorter amounts of time, you'll find that you will want to be part of the solution rather than the problem, or rather be on the outside of the problem, and you'll want to be participatory or actively engaged to help solve the problem, whoever's fault it is. And as you become more sophisticated or more advanced, you don't see things in contrasted us versus them, me versus that jerk, or, you know, you think less, I don't say combatively or belligerently, but you think more constructively, and that's good. You're converting that negative energy into helping solve the problem. And as we were already talking about, you know, Python is very open, very democratic, very focused on solving problems instead of dividing or thinking in more smaller-minded ways. Try and be part of the solution as you're failing fast, and that will come as you are failing fast.
Oh, that's certainly some helpful feedback.
Yeah, we got a little deep, I guess.
I like John's comment here. Learn to walk away for a moment, grab a Coke, walk around the block, and look at it with fresh eyes and fresh mindset. Yeah, I think that's good, John. I agree. Getting a Coke always works.
Yeah. I'd like to thank you both for your presentation this evening. Certainly informative. That I think that's the end of our presentation for tonight. Be sure to join us next month for our Dundermain meeting.
Cool. Well, thanks so much again for letting us share some stuff tonight, and hope everyone enjoyed it. And have a great evening, everyone. Cheers.
Thanks, JP. Thanks, Heather.